this therapeutic to the brain. And one thing I'm not showing on here, and I should add, is that the lysophospholipids, Michelle, the DHA containing lysophospholipids come into the brain. We now think that's probably the transport mechanism of reducing paper. I'll come back to that a little later. When I started in this field, we started taking advantage of genetic models. So the ideas are pretty simple, but if proof cannot be made in the brain, de novo, you need to transport them in. And if you knock out the receptor, and that's a major source by which fatty acids get into the brain, you'll lower the brain levels. So we did this with the LDL, the LDL receptor, and we really just couldn't get a phenotype. There was no effect. And I wouldn't conclude they're not involved based on that. All I would say is that they're not necessary. And not only are they not necessary, there's got to be some other mechanisms by which fatty acids get into the brain, because every lipoprotein receptor we look at has that in the phenotype. So I'm going to move into the free fatty acid pool, and some modeling we do based on what was done in Standard Rappaport's lab. We've got an in vivo model, so the animal's completely awake. We put catheters in the animal, a week or so before we do the experiment, and then we can infuse intravenously fatty acids, so free DHA, albumin, or free arachidonic acid, whichever fatty acid we want. We do this very quickly. We use computer pumps to control the rate of infusion so we can get to steady state quickly. We need to get to steady state to do kinetic modeling. We have to do this study within about 5 minutes. If you go too long, the liver takes up the free fatty acid and starts excreting it as lipoproteins, and then the tracer is literally everywhere in the blood, and you'll never be able to say that what you saw in the brain was related to what you infused because of the two lipids in the blood. We terminate the study, very importantly, at 5 minutes in the awake animal with a high-powered microwave, which really heats up the brain to 300 degrees. And we need to do that to stop all the activity of all the phospholipases, which continue and actually upregulate the activity post-mortem. The calculations are pretty straightforward. We measure the radioactivity in the brain, and we correct it for how much is in the blood of the animal over time. And this gives us incorporation coefficients. And if you know the incorporation coefficient of your tracer, you can just multiply that by the level of the fatty acid in the blood, and you can get uptake rates. And you can do some other modeling that I won't get into. So now 4 independent labs have done this. Well, we all come out of Stanley's lab, but we all background institutions have done this, and we all get rates. They vary a little bit depending on the diet. I've just taken some examples here. But in general, the rate of uptake of the free fatty acid pool into the brain is about 2 to 10 picomoles per gram per second. Some of the fatty acids that have lower rates here, this is their esterification of phospholipids, so the alpha-linolenic acid is entering, but it's beta oxidized, so that's why it looks a little lower there. So I put this back on our graph here at the bottom. I don't know if it's through a transport or a passive infusion mechanism, but they're coming in at 2 to 10 picomoles per gram per second. And quickly we realized that, is that a lot or is that a little? I might have been able to change these units to 20 to 40, and maybe nobody would call me out. Maybe I could change picomoles to nanomoles, which is not a trivial difference. And people have said, I don't know if that's a lot or a little. So we had to think about ways to kind of quantify this, these rates of uptake. Is this a lot or is this a little? And I'm going to move in now to some of our unpublished data, which is up on a poster if you want to know a lot more of these details about the chart. What we did is we started off by giving a radio-labeled DHA orally to the animal. And this labels all kinds of plasma pools, as you can see here. It gets all over the place. And then we measured the brain radioactivity at the end of this study. And we said, let's just assume that only the free fatty acid level is getting to the brain and we'll ignore the other pools. And we'll calculate an uptake coefficient for the brain. We'll call it 100%. Now, if we're right, that's the only pool getting to the brain. It's pretty straightforward. If these other pools are also getting to the brain, my uptake coefficient is going to be an underestimate, and it won't match with the real uptake, total uptake is. It's going to be sort of an overestimate. Then we do our free living infusion for 5 minutes with just the free fatty acid pool, just the free DHA being infused into the animal with our microwave fixation. And we calculate the uptake coefficient with this model. And it matches pretty much perfectly. If anything, it could be a little too high. But what it suggests is that all the brain radioactivity we saw after the oral administration of the tracer, when you labeled all these pools, can solely be predicted by the uptake coefficient of the free fatty acid pool. We took one more approach, and in this approach we infused DHA into the ventricle of the animal. You wait about 4 days, you let it label all the brain phospholipids, And then you follow the animals out over time, and you can see this then takes months, 128 days. And you get a slope, which is the loss of DHA from brain phospholipids. You get a slope, you get a half-life, you know how much brain DHA is in there, and you can kind of back calculate to a brain coefficient. And then in this case, we get, again, not all, but that most of the brain radioactivity that's being lost seems to be predicted by the rate of uptake of the free fatty acid pool. Definitely some room for some other pools in there, and there are errors to these numbers. I think it could be as high as 60 to 100% of the brain consumption is explained by just the free fatty acid pool. So I put this on here, and I think it's it's not the only source for the brain, but it's definitely a major source. Now, how does that fit with the hypothesis that lyso-PC-DHA is a preferential source for the brain? And I've been talking to Michel Lagarde, very fortunate with this, and working with him and He's in SC in the back, Michel. I think we're in similar agreement here that we're doing very different things. And one of this kind of approach might be very therapeutically relevant. So the idea is if you give a bolus of unesterified DHA or lyso-PC-DHA, the partition coefficient to the brain for lyso-PC-DHA is quite a bit higher, probably 10-fold higher than an esterified pool. But what we're doing is we're factoring in the half-lives, and sometimes people don't realize this, but unesterified DHA, although it might have a little partition coefficient to the brain, it's got a very short half-life. It's probably 20 to 30 seconds in the blood, whereas most of the lipoproteins or lyso-PC in the minutes, if not to hours. So it's kind of a lower partition coefficient to the brain, but very fast. So do they require a transporter, or is it a passive diffusion mechanism? CD36 was a major candidate for this. We tried to knock out the phenotype again. And there's Jim Hamilton has really shown something elegantly that I think CD36 is probably not a fatty acid transporter. It's probably about the metabolism of fatty acids and quenching fatty acids in the brain. We collaborated with Frederick Cologne in what's called the Tapasato method. It's an in situ method where you can perfuse radiolabeled DHA or EPA, and you can do standard biochemical competition assays. So we can infuse radiolabeled DHA, increasing the cold concentration of DHA, trying to outcompete the tracer into the brain. Very standard approach. So the idea here is the radiotracers in the red, we increase the cold concentration to a super physiological level, and if there's a transporter, we shouldn't see any radioactivity as we do the study of the high concentration. If it's just a passive diffusion mechanism, the radioactivity is going to be the same in all experiments. So you do the experiment, there's a radioactivity, DHA concentration is increasing. I'm not going to say there's no transporter, but this data doesn't support a transporter. The radioactivity really should have dropped if there clearly was a transporter. We don't see that. But more interestingly, when we did this experiment, is that the uptake rate of EPA was very, very similar to DHA. And this poses a bit of a problem because if their uptake rates are about the same, where's the EPA? It's virtually not detectable in the brain. And I'm just going to summarize this and post a plug for my student Chuck tomorrow night, who's presenting at the DSM lectures, because I think he's really figured this all out, all in vivo. It doesn't appear to be any selective uptake, but when EPA comes into the brain, it's rapidly. And the fastest we could physically do this was 40 seconds. And we can detect evidence of beta oxidation in 40 seconds. Most fatty acids go into the brain and they're recycled according to the Benna Issfal pathway. That's a high way to conserve fatty acids. EPA is not heavily recycled. When it comes out of the membrane, it's lost. We can't detect it anymore. You also get some conversion of EPA to DPA-3. And then, interestingly, when you start blocking these pathways pharmacologically to try to increase brain EPA levels, you fail because these pathways are multiple and redundant. So you block one and the other one compensates. And we haven't had an approach to block them all yet. Just going to summarize with a little bit of application. You can do this in rodents, and I've got Stanley and Norman here because they just get it in humans. They need gamma-labeled DHA, and they infuse it into some subjects in the Bethesda area, and this is fully quantitative. So you can get the unesterified rate of DHA entering into the brain. This is the first study they did. They also did in alcoholics where they had another control group, and in that study they got a rate of 2 milligrams per day of uptake into the brain. So somewhere between 2 and 4 milligrams of DHA into the brain per day. Now, if the assumptions are right that the unesterified pool is a major contributor, This is about how much DHA gets into the brain. If the assumptions aren't right, and there are other pools contributing to the brain that are quantitatively major, this number gets higher. So I think this is going to be important to figure out. Two things to say about this. The number's lower than I expected. You don't need to eat a lot of fish to get 2 to 4 milligrams per day. But I think it's got some important implications kind of clinically. Here's a slide from Bob McNamara's lab, and if you come over to the right, I'd like you to focus on DHA levels, postmortem samples, bipolar subjects. Don't worry about suicide or not. The levels are reportedly lower than bipolar subjects. It's percent composition, but if you do the math backwards, there's about a gram difference in the brain concentrations. Make a simple assumption that's not true. DHA is entering the brain at 2 milligrams per day with a gram difference here. It's going to take you 500 days to restore your levels, at best, because you've also got to consume some of that DHA for arterial dose. That's over a year to restore these levels. So, that's slow. Maybe the rates change in disease, maybe the brain consumption rates change in disease. To address that, we've kind of modified the method again from Stanley Rappaport lab, where we're interested in looking at the conversion rate of ALA to DHA. So not a fractional conversion, but an actual nanomoles per hour kind of rate. And what you do here, from the last slides, is you need to get plasma volume, and we've done 3 different diets, so a high ALA diet, a high DHA diet, and a controlled diet. You need to calculate the plasma volume and the appearance of deuterated DHA into the plasma after an oral, a steady state infusion of labeled ALA. You correct the levels, but the important thing is that DHA starts to appear according to a sigmoidal plot. If you have DHA in your diet, you completely shut down the synthesis. We actually can't solve these curves. But when you have a curve with a point in time, if you take some simple calculus and take the derivative of these, you actually get rates of nanomoles per unit of time being synthesized. And in our hands, anyways, in the rat, the synthesis rate of DHA is many, many times greater than the uptake rates in the same animal, suggesting that under normal circumstances, the ALA should be able to supply a fair amount of DHA. So we always say the ALA to DHA synthesis rate is very low, and I agree on that. 1% is not much. If you give me $100 and I give you $1 back, that's a terrible rate of return. But it depends what you need to buy with that dollar. If you don't need to buy very much, it might be more than enough. Now, this might all change in disease, this might change with aging, this might change, it probably doesn't apply to development where you've got a very big accretion of DHA in the brain. But we think we've got kind of the tools now to start looking at these questions to see, does the rate of DHA consumption in the brain change? Does the supply to DHA in the brain change? And if you have liver disease, can we make the DHA to supply to the brain? So in summary, I think I presented some evidence that the plasma unesterified pool rapidly enters the brain. These things are happening faster than we can physically measure them, and is quantitatively a major pool. I didn't show you much, but some of the big differences in fatty acid uptake levels in the brain don't seem to be explained by uptake levels. Across labs, all their uptake levels are relatively similar. And it seems to be this very rapid and extensive metabolism that explains fairly large differences in their levels. And then now we have the tools available to quantify this in rodents and start looking at some of the questions that Gino's asking. And we're starting to apply this in humans here. So I'd like to thank